All right, we are to the last section of Module C. And in this section, we're going to talk about radical equations and power functions. This particular video, we're going to review a little bit of our rules of exponents and radicals. And then in the next section, in the next half, we'll go ahead and look at some of the new material. All right, so when we talk about exponents and radicals, these are actually related. Just like multiplication and division are related, addition and subtraction are related, exponents and radicals are related. And so a lot of the rules that we have for exponents also apply to radicals. So the first thing that we have is we have a product rule. And so for our product rule, what we have is if you have two things being multiplied that have the same base, then what we can do is we can add the exponents. We also have similar ideas for radicals. If we have the square root of a times the square root of b, we can go ahead and combine it into a single radical by multiplying the insides. This applies not only to square roots, but any kind of root. As long as our index is the same, we can go ahead and combine into a single root, and we can go ahead and multiply the insides. The second rule that we have is the quotient rule. And so the quotient rule says that if you divide things that have the same base, then we can go ahead and subtract the exponents. We have similar rules for roots, and the basic rules are if you take the square root of a divided by the square root of b, then what you can do is you can divide the insides and then take the square root. And this applies for any root. If you have the nth root, we can also divide the insides and then apply the root. And finally, we have our power rule. Our power rule states that if you have a variable raised to an exponent, and you raise that whole thing to another exponent, apply the exponents. We have a power rule for square roots, and basically what this says is if you take b and you raise it to the n, and then you take the square root, it's going to be the same thing as long if you take the square root of b and then raise it to the nth power. So these are going to be interchangeable. You can decide which one you want to do first. Now remember that we do have the rule that we have to be dealing in the real number system. This is not true in the complex number system. Same thing applies for nth roots. You can either raise your base to the exponent and then take the nth root, or you can take the nth root of your expression and then raise it to a power of m. The next one that we have is negative exponents. Remember that negative exponents is our reciprocals. We basically want to just move things to the other side of the fraction bar, and then you can change the exponent to positive. Now we do want to talk about what's the relationship between exponents and roots. And so when we talk about exponents and roots, what we have here is fractional exponents. And so if you have a exponent of m in the numerator of your exponent, that stays the exponent. And then if you have a exponent in the denominator, or if you have a number in the denominator of the exponent, it becomes something we call the index. What kind of root is it? All right, so in this first section, these are going to be the things that we're going to play around with. All right, so the first thing we're going to do is we're going to go ahead and do some evaluating, and we're going to see that there are lots of different ways to do these things, okay? Well, maybe not lots, but we have a couple options. All right, so the first thing we're going to do is we're going to start with example A. In example A, what we have is 64 to the 2/3. Okay, so we're going to go ahead and convert to roots. We should be doing all of these by hand. And so if we convert this to a root, what we're going to have is 64. The numerator of my exponent stays an exponent, and the denominator becomes the type of root. And so this is going to be the cube root of 64 squared. Now, all of these problems we should be able to do without a calculator or having to do any real long computations by hand. Me personally, I don't feel like squaring 64 because that's going to be a really big number, and then trying to figure out what cubed equals that number is even worse. So what we can do is we can flip our operation around. I want to take the cube root of 64, and then I want to square it. So this is something that I can do without a calculator, and hopefully as you get better with this, you'll be able to do that as well if you can't already. All right, I want to know what cubed equals 64. Now some of you might say 8, but that's actually 8 squared equals 64. And so we want to go a little bit smaller. And so what we get is the cube root of 64 is actually equal to 4. 4 times 4 is 16, and if you multiply that by 4, you do get 64. All right, then we can go ahead and square the result, and we get 16. And we're done. All right, let's come over to example B. Example B, we have 8 to the negative 1/2 over 8 to the 5/6. The first thing that I want to do is I do want to kind of combine everything. And there's a couple different ways that you can do this. I prefer to avoid negatives. And so one thing to note is you can move things to the bottom, from the bottom to the top. You can also move things from the top to the bottom. And so what I'm going to do is I'm going to move my 8 to the negative 1/2 down to the bottom. And so what I'm going to get is 1 over 8 to the 5/6 times 8 to the 1/2. And again, you can do this in as many steps as you need. Now here we do have a multiplication. And remember that when we multiply things with the same base, we want to add our exponents. Now to make it a little bit easier, I'm just going to come over to the side and add these. We do need a common denominator. And my common denominator is going to be 6. So I'm going to go ahead and multiply this by 3. We get 5 plus 3 over 6, which is 8 over 6, which is 4/3. All right, I'm going to bring that back over to my expression. And so what we have here is in the denominator, we have 8 to the 4/3. All right, again, we want to use roots to simplify this. So I'm going to switch this to my denominator becomes the root. I need a little bit more room there. My denominator of the exponent becomes the root. And my numerator of the exponent is going to stay on the outside as an exponent. Okay, if we take the cube root of 8, we get 2. And we can raise that to the 4th. And 2 to the 4th is equal to 16. If we do 2 times 2 is 4, times 2 is 8, that's our cube, and times 2 is 16, which is our 4th power. All right, let's look at a couple more. Okay, if we look at example C, we have 27 to the 5/6 times 27 to the negative 1/6. Here, I'm going to go ahead and do my multiplication. You could change exponents to positives if you want. Again, there's lots of ways to do these. But when I look at this, I want to think about, okay, I'm just going to add my exponents. We have the same base, and so we want to add them. But 5/6 plus negative 1/6 is the same thing as 5/6 minus 1/6. And if we simplify that, we get 4 over 6, which we can simplify the fraction. It becomes a 2/3. All right, we can go ahead and convert this to radical notation. Again, the denominator in the exponent is going to become my root, and the numerator is going to stay as a regular exponent. All right, if we take the cube root of 27, we get 3, and 3 squared is equal to 9, and we're done. All right, next example. Let's come to example D. All right, so for example D, what we have is we have essentially an exponent raised to another exponent. And so remember that for this, what we want to do is we want to multiply them. So I'm going to start with that, and I'm going to come over to the side to do it. We get 3/4 times 2/3. And I can cancel some stuff. My 3's cancel. 4 and 2 are divisible by 2, and so what we get is that this is equal to 1/2. All right, 9 to the 1/2. All right, so when we write this, the denominator becomes the type of root. The numerator stays the exponent on the outside, but because it is a 1, we don't really need to do anything with it. Now, this is not a common notation for us. This is essentially just the square root of 9. This is one that we use so often that we usually don't write the index in there. And the square root of 9 is equal to 3. All right, last one. All right, we have negative 32 to the negative 3/5. All right, the first thing I'm going to do is I'm going to take care of my negative exponent. And remember that what we're going to do is we're just going to move it to the bottom. When we move it to the bottom, the exponent becomes positive. Okay, now we're going to go ahead and rewrite in radical notation. So the denominator of the exponent becomes my index. This is going to be a 5th root. We have our negative 32. And the numerator is of our exponent is just going to stay a regular exponent. Now, because we are talking a fifth root, negatives inside are allowed. So, the fifth root of negative 32 is going to be negative 2. Two times 2 is 4, times 2 is 8, that's our cube, times 2 is 16, that's our fourth, and times 2 is 32. This is still in the denominator. And then now if we cube negative 2, we get negative 1 over 8, or 1 over negative 8. And remember that our negative, we can always, in a fraction, we can always move the negative from the bottom to the top or even the front. All right, so that is our first round of examples. Okay, let's go ahead and play with some other ones. All right, so most of the time when we are evaluating, we do like to convert to radical notation. And it's just a matter of getting familiar with these things. But we can also go the other direction. And so what we want to do is we want to use rational exponents to write each one of these expressions. So for the first one, we have the square root of 2x. Remember that because it is a square root, my index is a 2. And so what we're going to do is we're going to take our 2x, the thing inside the radical. My outside exponent is now going to have a denominator of 2. And because there was no other exponents running around, it's going to be a 1/2. And this is all that we have to do. All right, our next example. We have the fifth root of x squared. All right, so my base is x. The index is going to become the denominator of my exponent. And the other exponent, the one that looks like a regular exponent, is going to become the numerator. And so what this is equal to is x raised to the 2/5. All right, our last example. We have the fourth root of y all raised to the -3. And I think that it said positive rational exponents. Okay, so let's see what we can do here. The first thing we're going to do is we are going to convert it to an exponent. The outside exponent is going to stay our numerator, and the inside, or the root, is going to become the denominator. Because it is asking for positive exponents, the last thing that we want to do is we want to just move this down to the denominator. And so what we get is 1 over y to the 3/4. And we're done. Now, later on, we're going to be talking about exponential and logarithmic equations. And when we talk about those, this is really when we want to be able to convert back and forth between radical notation and rational exponent notation. We are going to be doing this again later this semester. All right, the last thing we're going to do is we're going to bring in our functions and just see what we can do with this. So most of this is going to be very similar, okay? It's not going to be anything new. And so, for instance, example A, we want to evaluate each function. For example A, we want to know what is f of x equal to when x equals 8. So if we plug in 8, we get 5 times the cube root of negative 8. You are allowed to take the cube root of a negative. And so the cube root of negative 8 is negative 2. And if we multiply that by 5, we get negative 10. All right, let's come over to example B. Example B, we have g of x equals the square root of 2x cubed. And so if we plug in 2 for x, we get the square root of 2 times 2 cubed. We do want to follow order of operations. 2 cubed is 8. If we multiply that by 2, we get 16. And the square root of 16 is equal to 4. All right, last one. All right, we have h of x equals the fourth root of 5 times x. And for this one, what we can do is we're going to plug in our 125. There's going to be a couple things that we can do here. I'm going to show you 2 ways you can do this. We can go ahead and multiply. And if we multiply 5 times 125, well, what we get is the fourth root of 625. Now, I don't know a whole lot of my fourth powers, but I do know that this is going to equal 5. Now, as I said, we should be able to do all of these by hand. And so if you don't know that 5 to the 4th power is equal to 625, that's okay. Hopefully, you do know that 125 is equal to 5 cubed. We are seeing some relationships here. And so what we can do is we can go ahead and rewrite this as 5 cubed. Because we do have same bases on the inside, we can add our exponents and we get 5 to the 4th. And a general rule that we have is as long as we are dealing with positive numbers when we're dealing with even roots, if they are the same, then they do cancel. We've played around with this before. When we talk about square root property, we use square roots to get rid of squares. And in previous math classes, and we'll see it later on in this section, we use squares to get rid of square roots. And same thing with cubes and cube roots, fourth powers and fourth roots. These all cancel each other out. All right, that takes care of these examples. All right, the last thing that we're going to do is we are going to review our graphing radical functions, and we are going to use transformations. So I do want to kind of review that. All right, so to get us started, we want to go ahead and figure out some points that are on our cubic function. I'm sorry, cube root function. Just to make sure that we are consistent with our graph, I am going to pick values of -8, -1, 0, 1, and 8. These are all perfect cubes. And if we take the cube root of each one of these numbers, we get -2, -1, 0, 1, and 2. All right, I want to go ahead and describe what happens to our graph using transformations. So the first thing we want to know is, remember there is an order to this. Do we have any horizontal shifts? We do have a horizontal shift. And remember, shifts are the adding and subtractings. And because I do have a +1 on the inside, I do have a shift, a horizontal shift of 1. And remember, we always do the opposite of what it says. I want to actually subtract 1 from my x's, and so this essentially means I want to go left 1. All right, the next thing we have is we want to know if we have any stretchings, compressings, and reflectings. And so for here, we're going to look at our outside numbers. And so this -2 does two things. We have a vertical stretch by 2. And we also have a vertical reflect because of the negative. Now remember, vertical reflect is going to be about the x-axis. All right, after we do our stretching, compressing, and reflecting, then we want to know, do we have any vertical shifts? And we do have a vertical shift. It's going to be this -2 over here. And so we do have a vertical shift. And remember that vertical, we always do exactly what it says. This is saying I want to go down 2. All right, so let's start with our table and figure out what we're going to do. All right, when we look at our x's, we want to do all of our horizontal stuff. And so for left 1, we're going to subtract 1 from all of our x's. So we get -9, -2, -1, 0, and 7. So we are subtracting 1 from our x's. All right, for my vertical stuff, I'm going to do this in 2 steps. I'm going to do my stretching and reflecting first. And so remember what this means is I basically just want to take all of my y values and multiply them by -2. So -2 times -2, we get +4. -1 times -2, we get 2. 0 stays 0. 1 times -2 is -2. And 2 times -2 is -4. All right, so what we are doing here is we are just multiplying by -2. Now that's not all the vertical stuff. We still have our vertical shift. And so for our vertical shift, I'm going to do that as a separate table. We're done with all of our horizontal stuff, so our x's from the previous table will stay the same. And now we want to go down 2. So all of my y values, I'm going to subtract 2. We get 2, 0, -2, -4, and -6. All right, so now let's go ahead and graph this. All right, we have 0, 0, 1, 1, and we have 8, 2. That's going to be somewhere over here. And on the other side, we have -1, -1, and we have -8, -2 over here. And when we draw this, it should be that snake shape kind of laying on its side, and we should get something that looks like this. All right. The other graph that we want to do is going to be the final table that we came up with. And so what we have is negative 9, 2. That's going to be somewhere over here. We have negative 2, 0. We have negative 1, negative 2. We have 0, negative 4. And we have 7, negative 6. And when we graph this, we have that our snake shape has been reflected. So we have flipped it. And we've also done some stretching and some shifting. All right, so we are going to continue to play around with these transformations. And so we'll go ahead and see them when we talk about radical functions. All right, that takes care of this video. We have one more video for this section and for this module, and so I will see you again soon.